Good morning, everyone. Today we are going to look at how to measure risk in epidemiology. Now, risk is a very important concept to be understood by those taking epidemiology and public health. When we talk about risk usually implies probability of an outcome, usually negative outcome, in a specified period of time. So as I said, it's a quantifiable concept. So for example, the risk of suffering from a heart attack and the risk of dying from a heart attack. So the words probability or likelihood or risk are used interchangeably to define the concept of what we call as risk. Now, the problem is, why is it so important to know about risk? Now, when we talk about the practice of public health, we have kind of choices to be provided to the population. So a quantitative estimate of risk will help us provide the evidence to make an appropriate public health choice or to make decisions about the course of action or intervention, as well as how to allocate scarce resources like time and money and be efficient in getting the output. So that's about understanding risk. Now, what is the relationship between risk and association? When we talk about epidemiology, association means a correlation between an exposure and an outcome. So here we will talk a bit about what is correlation and what is causation. Now, it's a common mistake to say that an exposure causes an outcome without actually having understood what is the interaction between an exposure and outcome. So we need to understand what's the difference between correlation, also known as association, and causation. So correlation is a situation where the variables means our exposure and outcome, they change at the same time. For example, when exposure to sun increases, incidence of certain types of cancer increases. So what's important to remember is that just because both the variables change, it does not mean that one causes the other to change. In other words, causation does not relate to correlation, or correlation does not imply that it is causation, because there may be some unknown factors which may cause both the exposure and outcome to change. But deciding the degree to which an association may be causal is a great deal of an epidemiologist's thinking and effort. For example, where an association is thought to be causal in nature, what we do is we use the word risk factor. So, for example, if we talk about smoking and lung cancer, so what happens here is smoking is our exposure and lung cancer is our outcome. Now, the question is whether smoking causes lung cancer. So, measures of association which are used in order to study these relationships, whether it is association or causation, are going to be discussed in the next slides. So let's look at what are the measures of association which we are going to look at today. They are relative risk, also known as RR, odds ratio, known as OR, attributable risk, known as attributable risk AR, population attributable risk, known as PAR, and population attributable risk percentage or population attributable risk proportion. Before we actually go on to what are these risks and ratios, we need to get the concepts of ratios, proportions, and weights clarified, so that there is no confusion as to understanding what is a rate and a ratio and what is the difference between these three terminologies. So let's look at starting with ratio. So a ratio compares two dissimilar things by dividing one quantity by other. So what in other words we do is we compare two variables. So let's look at an example. If we have a group of 12 individuals, we can take a ratio of females as to males. So in this case, the ratio of females as to males is 5 as to 7. What's a proportion? In a proportion, we have again a numerator and a denominator. However, the point to remember is numerator is included in the denominator, or in other words, numerator is a part of the denominator. So if I have to find a proportion of women in the example which we use for ratio, we will say it will be 5/12, which is equivalent to 0.42. Now, in order to understand this better and to remove the decimal, we can express this as either 42 per 100 or 42% women. So proportion is nothing but a percentage. So we consider it as part of the whole. So how many women form the complete group of 12 individuals is nothing but the proportion of women in that particular group. Next, we move on to what is a rate. Now, a rate is known as a proportion related to time. So, the point to be noted for a rate is it will have a time factor and it will also have a multiplier. Now, generally, for rates, we use person years as the denominator. So, we count the number of people during specified period of time to calculate what we call as a rate. And as an example, if we find that the rate is 0.00081 maybe deaths, so how do we put it as express it as a rate is we express it as 8.1 deaths per 100,000 population. So expression of a rate is per 100, per 100,000, per 10,000 population. Whatever is the event, whether it is deaths, births, or maybe anything else. Okay, so how now does this go ahead is we use a constant multiplier. So we need to remember here that either we use multiples of 10 in the form of 100 or 1000, 10,000 or 100,000, but we have to be very clear on what we are using because the numbers would change accordingly. So as we can see here, 8 deaths per 100,000 could be expressed either as 8 per 100,000 or 0.8 per 10,000 or 0.008 per 100. They all mean the same, but the most important thing is we express it per multiples of 10 of the population. So that's very important to understand about ratios, proportions, and rates. We move now next to an important concept which we need to understand before we move on to calculation of the risks and the ratios. We use 2 by 2 tables, which are also known as contingency tables for studies in epidemiology, and they help us record and analyze the relationship between the exposure and the outcome. Okay, so what we generally compare is we consider 2 states of exposure and 2 states of the disease when we make a 2 by 2 table. What is the meaning of 2 by 2? 2 by 2 is this table has got 2 rows and 2 columns. That is the format of these tables. So conventionally, the outcomes or what we call as the disease are put under columns. So one column would be people who are diseased and the other column will be people who are not diseased, whereas the exposures are put in the rows. So there would be one row for the exposure and the second row for no exposure. Please remember that the numbers in each of the cell are practically counts of people who have been included in the study. There is no percentage, no proportion or no ratio expressed in each of the cells. So they are mere frequencies or counts of the exact data. So if we have to look at a 2 by 2 table, it's given like this. So you have 2 rows and 2 columns. So conventionally, as I said, the disease status comes along columns and the exposure status comes along rows. So this is about a 2 by 2 table. And this is quite important to make before you go on for calculation of any measure of association and calculation of risk. Now, before we actually go on to calculate risk, we need to look at from where are we going to get this information or these sources for calculating risk. So we can get figures from published studies or published data from health centers or health authorities which have been put on paper and which are known to the general public. But we can also get the information from doing epidemiological studies. And the calculation for risk all depends on what type of study design you adopt. So if you look at incidence rate, Incidence is nothing but the number of new cases of a particular disease in a year divided by the total population at risk. And this is expressed either as per 100 or per 1000 or 10,000 or 100,000 population. So this incidence rate can be calculated from what we call as a cohort study, because in a cohort study we try to look at development of new disease in the study groups. So that's incidence rate. There is another form of incidence rate which is known as an attack rate. It is a specific form of incidence rate which is generally calculated in when we study epidemics. So when we talk about attack rate, we look at the number of cases of illness which occur during an epidemic. So for example, if 100 people ate at a restaurant and 20 of them fell sick, 20 over 100, whatever per 100 or per 1000 population would give you the attack rate of that outbreak or that epidemic. So we need to remember that attack rate is a special form of incidence rate. The next one is death rate. So death rate is nothing but the number of deaths in a given year over the total population. So these are the sources from which we can calculate risk. So these are the different types of rates which we have seen for which helps with calculations. Now, interpretation of risk is a major thing, and we need to understand this with reference to data. Now, most of the times when we look at reports or we look at news stories, we need to check for with ourselves whether all these statements are based on rates or are they based on proportions, especially if we are looking from data from sources like inpatient records of hospitals. We need to be very, very careful. Now, if you look at this example which is given here, it talks about the age distribution of stroke cases from a hospital. So you can see that there are different age groups given here, and for every age group the number of cases of stroke which have been admitted to that hospital have been computed. And the next column shows you the percentage of these cases in every age group as compared to the whole population admitted to that particular hospital. So what we can understand here is we do not get a risk based on the data given here. The reason is because this particular data is based only on proportions, and it gives you a proportion of cases in one facility, that is in a hospital, and not for all the people who are at risk in that defined population. Because the problem is, for in a city hospital there may be people coming from different areas, different age groups, different maybe races or ethnicities who are admitted to that particular hospital. So it may be very, very difficult to define what the population is from where these cases came from. Okay, so now if you look at this data, it may be tempting to say that the risk of dying is highest in the age group of 60 to 69 years. So the risk of dying from stroke is highest amongst the 60 to 69 year age group. But the point to remember here is we do not know for every age group what is the population at risk which can suffer from stroke and die from stroke. Which, in other words, we cannot get a denominator to calculate the risk for any of these age categories. So for none of these age groups do we have a denominator to get a rate. Okay, although we all know in general that the risk of stroke increases with age, but we cannot use this information to reinforce our assumption because there could be other reasons for the number of strokes. It may happen that if you look at this, the younger age group here, it may happen that many of these people may have left the place and they may have gone for employment opportunities or maybe have gone for education, which would mean that the denominator for this age group would be smaller as compared to the denominator for this age group, wherein people would like to stay where they are, they wouldn't move out and so on. So what the point I'm trying to make over here is, please notice in any report or any record whether they have used proportions or rates when talking about risk. Please remember, proportions cannot be used to make statements regarding risk. So check whether these statements are based on rates, interpret records with caution because we do not know what is the total population at risk, and check if the report has got proportions or rates. Proportions cannot be used to define risk. This is the point which I want to make and I want to reinforce again and again. Now let's look at relative risk. So what is relative risk? So we are going to consider first the relative risk. It is nothing but a ratio. Please remember the word ratio of an event. Now what is an event here? So if we look at occurrence of disease as an event or development of disease as an event, we try to look at the risk of this event in two groups of people. Now who are these two groups? The one group is the people who are exposed to some factor, whichever we are studying, and the second group is the people who are not exposed to the factor which we are studying. So relative risk can be expressed as a ratio of persons exposed to the persons unexposed. It is also given by the formula incidence of the disease in the exposed over incidence of the disease in the non-exposed. Now, we need to remember one thing, that the size of the relative risk, the magnitude of the relative risk is one of the criterion which we use to estimate the strength of causal relationship between an exposure and outcome. So, larger the relative risk, stronger is the evidence of a causal relationship, everything else being positive or being equal. Okay, so for example, a relative risk of 10 provides a better evidence for a causal relationship as compared to a relative risk of 3. Okay, but remember one more thing, just by having a large relative risk, we cannot infer causation. There are other criteria which are known as Hill's criteria, which also need to be applicable in that particular scenario. Okay, so that's very important. Now let's look at how to interpret relative risk. Relative risk is equal to 1 means there is no evidence of an association between the exposure and the disease. If the relative risk is greater than 1, we can say that the exposure is harmful. So those who are exposed are at a higher risk of suffering from the disease compared to those who are not exposed. And if the relative risk is less than 1, we generally infer that the exposure may be protective. An example of this would be providing vaccine to a particular group and not providing vaccine to another group. So providing vaccine in this case becomes your exposure, and not providing your vaccine gives you no exposure. So if you get a relative risk in this calculation which is less than 1, you can then infer that the vaccine, providing the vaccine or administering the vaccine is protective, so it protects against causing disease, which in other words it means that number of people falling sick after getting the vaccine in them would be lesser as compared to number of people falling sick if they do not receive the vaccine. So that's all about interpretation of relative risk. Now let's actually move on to how to calculate relative risk. Going back to the previous slide, we said that relative risk is calculated by dividing incidence in the exposed by incidence in the non-exposed group. So let's look at an example, a hypothetical example. And this is an example of a cohort study which has been done on factory workers who have been exposed to toxic substances. And we are trying to look at development of lung disease in these factory workers. And what we will try to compare is the incidence of lung disease amongst those who are exposed to the toxic substance and the incidence of lung disease amongst those who are not exposed to the toxic substances, for which we have, you can see here that there is a 2x2 table given here. So these are the figures in each cell. So we can see there is a 2x2 table with 2 rows and 2 columns with the disease along the columns and the exposure along the rows. So giving our formula for relative risk, we will first calculate our numerator, that is incidence in the exposed group, which says that is incidence of lung disease amongst all those who are exposed. So it is 800 over 1000, and incidence of the disease amongst all those who are not exposed, that is 40 over 2000. So we got the incidence in the two groups, incidence of lung disease in two groups, in the exposed group and the not exposed group. So this is the calculation for the individual incidence. So we get 80% and 2%. You can express it either 80 per 100 or 2 per 100. Okay, and or you can express it as per 1000 also. And what we do next would be, we take a relative risk, that is divide incidence among exposed over incidence among non-exposed to get a number which is relative risk, and in this case it is 40. So what is the meaning of the word 40? Going back to the interpretation, we said that if the relative risk is more than 1, which in this case it is, we say that there is a possible link between the exposure being associated with the disease, or those who are exposed are at a higher risk of suffering from a disease, and here the risk is around 40 times as compared to those who are not exposed. So this is what is the interpretation. Exposed workers are 40 times more likely than the unexposed workers to develop lung cancer, lung disease. So please remember, relative risk, since it is based on incidence, we can calculate the relative risk only in cohort studies, because cohort studies are the ones which look at development of new disease. In other words, they are the ones which can help us calculate incidence. So relative risk can be calculated only in cohort studies. Now, point to remember over here is, you can see here that the relative risk is like 40 times higher amongst the exposed group. But again, we need to remember that this is not enough to prove causal relationship between exposure to the toxic substance and developing lung disease. So this is what we need to remember. Let's look at some key points of relative risk. Relative risk is a likelihood of an event, especially a disease, in people who are exposed to some factor compared to another group that is not exposed. This is the formula for relative risk: incidence in the exposed over incidence in the non-exposed. The point to remember is that relative risk is a ratio. Why I say it's a ratio? Because you are trying to compare two non-related things. We are trying to look at incidence among exposed and incidence among non-exposed, which are two totally different groups. The other name for relative risk is a risk ratio, because it is not a rate, please remember, it's a ratio. It does compare two rates, that is incidence rates among exposed and non-exposed, but ultimately the number is what we call as a ratio. So these are the things about relative risk we have seen. Let's move on now to odds ratio. Now, when we talk about odds ratio, we need to remember that calculation of odds ratio refers to taking a cross product of the cells or the numbers in the cells. Okay, now we saw that relative risks are done for cohort studies, but odds ratios are calculated for case control studies. Now the reason why we calculate an odds ratio in a case control study is because case control studies include people who already suffer from the disease. So we cannot get incidence of a disease in a case control study. So what we get is prevalence of the disease, and the measure of association we calculate in case control studies is known as a odds ratio. Now we need to remember one more thing, that the calculation of odds ratio or the value of odds ratio we can use to approximate relative risk in case control studies. So we can be very close to the estimation of relative risk if we do a case control study when two criteria are satisfied. First one is if we perform what we call as matching, wherein we try to match or we try to make the cases and controls as similar as possible other than the disease status. So if we perform matching and we calculate an odds ratio, we can calculate an odds ratio which is quite a very close estimate of relative risk if we would have done a cohort study using the same exposure and outcome. And secondly, we need to remember that the disease should be rare. So in these two conditions only, we can say that OR can be used to approximate relative risks. So now let's look at how to calculate to calculate odds ratio. Now we will look at a hypothetical data wherein we are looking at deaths occurring by suicide in Washington state from 2003 to 2005. So my research question is, does higher suicide rate in men have to do anything with whether they lived alone? So here we can see that suicide is our health event or outcome, and living alone or not living alone becomes our exposure and no exposure status. Now, if we make a 2 by 2 table over here, we can see here that suicide, yes, means those who commit suicide, no is don't, those who do not, living alone and not alone, and these are the numbers in each of the cells, and these are the totals for the rows and for the columns. So a calculation of an odds ratio is simply we take a cross product of A into D, that is the cell which says those who have the health outcome and are exposed, multiplied by those who do not have the outcome and are not exposed, and this cross product is divided by another cross product which is known as those who are not having the health event but are exposed, and those who are having the health event but not exposed, and we take simply a ratio of these two cross products. So odds ratio is also known as a cross product ratio. The formula for odds ratio is A into D over B into C. So in this case, if you do a cross product ratio, we get 48 into 88 divided by 12 into 52, which gives us an answer of 6.8. So how do I interpret this? Living alone increases the odds for suicide in men by a factor of 6.8. So we use the word odds, or we can say that it increases the chance for suicide in men by 6.8 times as compared to men who are not living alone. So that's about odds ratio. So key points about odds ratio. Odds ratio approximates RR under two situations. These are the two assumptions or situations. You need to have cases from the same population as controls, and we need to do matching, and the disease has to be rare. Odds ratio is calculated in case control studies, and this is the typical 2 by 2 table for odds ratio. The formula for odds ratio is A multiplied by D over B multiplied by C. So to summarize, for risk is a probability of an outcome. Relative risk is calculated in cohort studies, which are also known as incidence studies. Relative risk gives us the strength of association between an exposure and the disease. But point to remember is that larger relative risk does not prove causation. It will help us prove causation, but it is not the sole factor which can prove causation. Odds ratio, on the other hand, are calculated in case control studies, and it will approximate the relative risk in certain situations which we have already seen. Now let's move on next to what is an attributable risk. If you remember, we said that relative risk is a likelihood of an event or a disease or an outcome occurring in people who are exposed to the risk factor or exposed to a factor as compared to another group which is not, right? But attributable risk, when we talk about, is more concrete, and it is expressed as an absolute rate of a disease and not as a ratio. So the point to remember is relative risk is a ratio, but attributable risk is an absolute rate of the disease. Okay, so what it is actually is, it is a rate or incidence of a disease in the exposed group. So we are concentrating now here on the exposed group, and that rate can be attributed to the exposure itself. So we are talking about incidence of the disease in the exposed group here. So as I said earlier, it gives you an absolute amount of the disease. So number of cases of the disease amongst those who are exposed gives you the attributable risk, which results from the exposure. And we need to remember that it is expressed as cases per multiple of population. So going back to our basics of rates, ratios and proportions, we said that rates are expressed as multiples of the population. So we express it as per 100, per 1000, per 10,000 or 100,000 population. Because attributable risk is a rate, you need to remember that you express it in this format. Now, the usefulness of attributable risk is we use it to determine amount of disease that could be eliminated by removing the exposure, because we are looking at how much is the disease occurrence in the exposed group. We also look at what if we remove the exposure, how much of the disease can we prevent. So point to remember is that attributable risk is mainly used for planning prevention strategies and to look at how much disease can be eliminated by removing the exposure. Now, let's look at the calculation of attributable risk. We calculate this attributable risk by subtracting the incidence in the unexposed from the incidence in the exposed. So this is a calculation wherein we subtract one incidence from the other. Okay, so if we have to look at the example of the factory workers wherein we talked about exposure to toxic substance and developing lung disease which makes them sick, or not developing lung disease which considers them as well. um, we said that initially 800 of those workers who fell sick were exposed from those who were totally exposed. So what is happening here is 40 of the non-exposed ones out of 2000 they develop the disease. Now we remember that the incidence of the lung disease in the exposed group was 800 over 1000, and that amongst the non-exposed was 40 over 2000. So now if since we have to use incidence rates with same denominators, we will have to convert this 40 over 2000 as per 1000, because we have 800 per 1000, so we need to convert this 40 over 2000. So if we give incidence of lung disease among exposed, we get 800 over 1000, and incidence of lung disease among non-exposed gives us 40 over 2000, or in other words it gives us 20 over 1000. Now to calculate the attributable risk, what we do is simply 800 minus 20, which gives us 780 cases of lung illness per 1000 people per year. So if you look at this, we express it in the form of a rate. So attributable risk is an absolute amount of the disease. So we are looking at 780 cases of lung illness per 1000 people per year. Now, usefulness of this attributable risk. Now to explain this usefulness, I have used this example wherein this is a very old study which was done in 1956 about lung cancer and smoking in British physicians. So it was a study done amongst doctors to check for lung cancer and smoking as an exposure. So you can see here that the heavy smokers, they faced a relative risk of dying from lung cancer which is around 24 times as compared to those who are non-smokers, right? But the same group who are heavy smokers and non-smokers, in them the relative risk of suffering from a heart disease is only 1.4 times amongst the smokers as compared to non-smokers, right? So how did we get it? Here you can see that these numbers are nothing but the incidence rates given for lung cancer amongst heavy smokers and lung cancer among non-smokers, and similarly for heart disease. So to calculate the relative risk of death from lung cancer, we do nothing but a ratio of 166 to 7, which gives us the answer. And similarly, we do it for heart disease. We divide 599 over 422, which gives us the relative risk for dying from heart disease. So, what if we only calculate a relative risk here? We can infer from this that the relative risk of dying from lung cancer is much higher among smokers as compared to non-smokers when we compare it with the heart disease status. So the relative risk of suffering from heart disease among smokers is not that high as compared to the relative risk of dying from lung cancer. So what is important here is, what I'm trying to say here is, if we calculate only the relative risk, we do not calculate attributable risk, we will miss a crucial point. And what is that crucial point? Now let's first look at, if we calculate the attributable risk for both these conditions, you can see here that the attributable risk for heart disease due to smoking is much higher as compared to the attributable risk of lung cancer in that particular population. So as we all know, what is the formula for attributable risk? We subtract the lung cancer death rate in non-smokers from that in the heavy smokers. And what we see here is heavy smokers are more likely to die of heart disease than of lung cancer. What I mean here is smoking can be attributed more to heart disease rather than lung cancer. Why I say so is because heart disease presumably has got many other causes besides heavy smoking. We all know because it is a multifactorial causation. However, we need to understand here that if we were to eliminate smoking, attributable risk tells us that more people would be saved from death from heart disease rather than from lung cancer. So we can prevent more uh, deaths caused by heart disease due to smoking as compared to the lung cancer deaths if we eliminate smoking as the risk factor. Now, this is quite important when we plan for anti-smoking campaigns, because then we would have to concentrate more on heart disease as compared to lung cancer, because then we say that for a bigger population, removing smoking as a risk factor for heart disease death is equally important as considering stopping smoking for prevention of lung cancer. So we focus on heart disease more as compared to lung cancer when we want to design a public health program like an anti-smoking campaign or prevention of heart disease or prevention of lung cancer or prevention of cancer in general. So what are the key points for attributable risk? Please remember, it's an absolute rate of disease given by this formula: incidence in the exposed group minus incidence in the non-exposed group. Next, we move on to what is an attributable risk percent. Sometimes it's more useful to express an attributable risk as a proportion, as a part of the whole, or as a percentage. And to calculate attributable risk percent, we use the formula for attributable risk, that is, it is used as a numerator, and the denominator is the risk in the exposed group. So, for the same example we looked at earlier, that is an example of the British physician study about lung cancer and smoking. If we calculate the lung cancer attributable risk proportion, which we can get by using this, putting these figures in this formula, we get it as 166 minus 7 over 166. So what answer we get here is 96%. Now the point to remember is attributable risk is a rate. However, attributable risk is a percentage or a proportion. So it is expressed as a percentage. Okay, or you can express it as per 100. Similarly, for heart disease, the attributable risk proportion would be 30%. Now, when we compare the attributable risk percentages for deaths due to lung cancer and deaths due to heart disease, what it appears to us is by eliminating smoking, we would reduce a larger percentage of deaths due to lung cancer than of deaths due to heart disease in smokers. But as I said before, since frequency of heart disease deaths in the general population is so much greater than the frequency of lung cancer deaths, more heart disease deaths would be prevented, although the relative risk of dying of heart disease in smokers as compared to non-smokers is smaller. So this concept has got different dimensions. When you look at it from the point of view of populations, you need to understand that depending on how frequent the disease occurs in the population, it would determine the attributable risk. So it is with reference to the population we are talking of when we calculate the attributable risk and the attributable risk percentage. Now there is another concept known as population attributable risk. Now the previous studies we have looked at looks at samples drawn from populations. But if we are aware about the death rates due to lung cancer in the general population and also in the non-smokers, then we can calculate the risk in the general population of lung cancer deaths attributable to smoking. So how do we calculate the population attributable risk? It is given by the formula incidence in the general population minus incidence in the unexposed population. So if you look at the formula for attributable risk, we used here incidence in the exposed, whereas for population attributable risk, we use the incidence in the general population. The second part of the formula remains the same. Okay, so what is population attributable risk? It is an amount of risk which would be eliminated from the general population if the exposure were eliminated. So in population attributable risk, we talk about risk in terms of the general population. We do not talk about only the exposed or only the unexposed. We talk about the general population. Now, for example, if we have incidence of a particular disease in the general population as incidence of deaths in the general population is 62 per 100,000, and if we have the incidence of deaths in non-smokers as 7 per 100,000, to calculate the population attributable risk, what we will do is we subtract the incidence in the non-smokers from the incidence in the general population, which gives us a value of 55 deaths per 100,000. So point to remember again is that population attributable risk is also expressed as a rate like we had for attributable risk. Now we can also calculate another parameter which is known as population attributable risk percentage, wherein similar to attributable risk percentage, we take the denominator as incidence in the general population. So if we have to do it for this example, the population attributable risk comes to around 89%. So this is the formula for population attributable risk. The point which popped up here is all this calculation will help us guide public health decision making. What I mean by that is whether a public health program has to be designed for the given population or not all depends on what is the population attributable risk and what is the population attributable risk proportion for that particular disease in the study. Okay, so that's about population attributable risk. Now looking at what are the uses of relative risk and population attributable risk in public health practice. Going back to the example of exposure to toxic substance in a factory and occurrence of lung disease in the workers, we have already calculated our relative risk as being 40, right? Now things to remember, relative risk is important when we talk about causation, and it is a critical measure for researchers who try to study relationship between an exposure and outcome, whether an exposure causes an outcome or an exposure is associated with outcome or not. Whereas looking at population attributable risk, this risk is important for practitioners, people who treat patients or people who look at disease in general populations. And this risk, this measure helps us to allocate resources, as we all know that the resources which are available for preventing disease or improving health are limited. So time, money, manpower, material is limited. So by knowing the population attributable risk for a certain condition, we can decide on whether resources need to be put in for management of that particular outcome or for prevention of that particular outcome. So it helps basically in guiding us in making policy decisions about public health. Now, this is a calculation which has been given for the same example we saw earlier. We saw the relative risk of 40. If we calculate the attributable risk percentage for this particular study, we get it as 800 minus 20, which is derived from 40 over 2000 over 800, which gives us an attributable risk proportion of 98%, due to the exposure. Population attributable risk can be calculated in this case. Now, how do we do this? Is we can see here that the town population is given as 100,000. So from this, I can calculate the incidence of the disease in the general population. And how do I get it? I take the incidence of lung cancer, okay, and lung disease, and I divide it by 100,000, and what I get is 28. Similarly, I talk about incidence of the disease in the non-exposed, which comes to 20, and when I subtract it, I get 8. population attributable risk percent by taking the denominator as 28 and then I get it as 28.5. So how do we interpret this? We can see here incidence in the community or general population is 28 per 1000. So it means that elimination of toxic substances in this factory. So if you protect the factory workers from this exposure, then what will happen is in the general population, the disease will be reduced by 28%. So by eliminating the exposure even in a factory, you can reduce the population attributable risk in the general population by 28%. So that is the utility of understanding population attributable risk. Though only a few people may be exposed on account of their occupation to this particular toxic substance, nevertheless it still exists in the environment and people who are staying in the nearby locality are likely to suffer from that particular condition. So if this exposure is controlled, then even in the population you can prevent disease. So that's the magnitude of understanding population attributable risk. Key points to remember. Attributable risk is the absolute risk of disease in people exposed to a risk factor which is attributable to the exposure. It is attributable risk proportion. In this, what we do is we calculate the attributable risk and divide it by incidence rate in the exposed group. Population attributable risk gives us amount of disease that would be eliminated from the general population if the exposure to that disease were eliminated. So it talks more about prevention of disease in the general population. And population attributable risk percentage is calculated by dividing population attributable risk by incidence in the total population. So the difference between attributable risk and population attributable risk is population attributable risk takes the general population into account, whereas attributable risk only takes the exposed population into account when you make the calculation. So in summary, we talked about risk, which is a probability or a likelihood of an outcome. Generally, we say it's a negative outcome in the form of a disease or death. Relative risk is a measure of association which helps us measure the strength of association between the exposure and the disease. Larger relative risk value does not prove causation, but it gives an evidence that there is a strong relationship between the exposure and an outcome. Attributable risk AR measures absolute amount of disease attributable to an exposure in the exposed. It can also be expressed and calculated as a percentage known as attributable risk percentage or proportion. Population attributable risk again measures absolute amount of disease attributable to an exposure. Sorry, this is a mistake. It's not in the exposed, but it is in the general population. That can also be expressed and calculated as a percentage known as PAR, percentage or proportion. And odds ratio is a measure of association calculated in case control studies which approximates relative risk if matching is done and if the disease is relatively rare. So that's all about measures of association and measuring risk in epidemiology. Thank you. Keep watching and do subscribe.